Hello, and thanks for listening to this video. My name is N.Zagli, and I will be speaking about linear response theory and critical phenomena for the thermodynamic limit of multi-agent systems. This work has been done in collaboration with Gregorios Pavliotis at Imperial College and Valerio Lucarini at the University of Reading, and can be found in these two papers that I've listed here. There are two key messages in this presentation. The first one is that multi-agent systems can exhibit two different critical phenomena that we named critical transitions and phase transitions. Both of these phenomena are characterized by a pathology, which is a singularity in the linear response of the system. In particular, we focused on weakly interaction diffusions, and you can think of weakly interaction diffusions as big systems composed of n identical subsystems. Each of these subsystems has the same local dynamics given by a smooth vector field F, and all these subsystems are coupled together, and on top of this, you have noise that can either be additive or multiplicative. The key features of weakly interacting diffusions is that you have a null-to-all coupling and that the strength of the coupling is inversely proportional to the number of particles. So as the number of particles increases, you have more and more links, but of weaker and weaker strength. Weakly interacting diffusions describe both equilibrium and out of equilibrium processes, and the interesting features arise in the thermodynamic, which is sometimes called mean field limit. So I want to spend just a few words on this. One can take the thermodynamic limit by studying the empirical measure. So rather than looking at the state vector of the system, you look at the proportion of agents that are in a specific region of the phase space. And a standard result says that this empirical measure converges as the number of particles increases to infinity to a one particle distribution in some weak sense, whose dynamics is governed by a nonlinear Fokker-Planck equation, sometimes called McKean-Vlasov equation. Being a nonlinear Fokker-Planck equation, standard results do not apply, and we might have multiple coexisting stationary measures of these systems, this equation. And actually, the exchange of stability of these measures can be identified as phase transitions of the system. Our work focused on quadratic interactions, which physically means that all the agents, all the subsystems are nudged towards the center of mass x bar of the system. And in particular, we looked at two models, the Desai-Zwanzig model, which describes an equilibrium order-disorder phase transition that you can think of as a continuous analogous of the Ising model, and the BCM, the Bonilla, Casado, Morillo model, which describes an out of equilibrium self-synchronization transition of an ensemble of nonlinear oscillators. Both of these models show a second order phase transition, and we can study that because we know in this case what the order parameter is, which is the first moment of the stationary distribution. And in panel A of both figures, you can see that there is a continuous phase transition. It is interesting that in panel B, you can see the fluctuations, and the fluctuations are finite, the phase transition. So we were interested in how the system responded to perturbations. So if you think that you have a stationary state, which is characterized by a stationary measure, rho naught, and a constant value of the order parameter of the magnetization, then you can imagine of perturbing this state by adding a small perturbation, which is both time-dependent and possibly state-dependent. And then after lengthy calculations, you can evaluate the response of the order parameter of the magnetization in the frequency space. And you would end up with an equation which has the usual structure of linear response, which is a multiplication in frequency space of a susceptibility, gamma tilde, which we called macroscopic or renormalized susceptibility, and the Fourier transform of the time-dependent perturbation. In this case of the thermodynamic limit of weakly interacting diffusions, the macroscopic susceptibility can be written as a matrix multiplication of a matrix of the renormalization matrix Pij, actually the inverse of this, and the microscopic susceptibility gamma. And the renormalization matrix can be written as the identity plus a term that depends only on the coupling and multiplied by another microscopic susceptibility. All the microscopic susceptibilities can be written as a Fourier transform of microscopic response function, which has the usual structure of a fluctuation dissipation-like theorem, in which these response functions can be written as suitable correlation functions at the stationary unperturbed state. Being correlation functions, the operator L-DAGA, which can be identified as the transfer operator associated with the stationary state, appear in these formulas. But the main formula here is the one for the macroscopic susceptibility that determines the response of the system. And as you can see, a singularity in the response can arise both from the renormalization matrix and the microscopic susceptibility. If a pole for real frequencies appears in the microscopic susceptibility, then we have a critical transition. And this is related to the fact that the spectral gap of the transfer operator is shrinking to zero. And this is the standard framework for critical transition, in which you have a critical slowing down, a divergence of correlation properties, and a divergence of fluctuations at the critical transition. On the other hand, in these systems, a new class of transitions arise, which we call phase transitions, and these are due to the fact that the pole arises in the renormalization matrix Pij. In this case, the spectral gap is finite, and we have no divergence of correlation properties. And this is a genuine thermodynamic phenomenon because it happens only in the thermodynamic limit, and it arises from the coupling between the agents because it is related to the renormalization matrix. Anyways, in both cases, linear response theory breaks down and develops a singularity. Actually, linear response theory provides a lot of information about phase transitions even for finite systems. So through linear response numerical experiments, we obtain the macroscopic susceptibility for the Desai Zwanzig model, which is plotted in this figure. And in black and blue lines, you have the macroscopic susceptibility away from the transition. In red lines, the macroscopic susceptibility at the transition. And you have different lines because we have performed these experiments for different values of n. Away from this transition, you can see that there is no dependence on the number of particles. The system has already reached the thermodynamic limit. At the phase transition, we can actually see an increase of the susceptibility. And this is due to the fact that a pole in omega equals to 0 is arising in the thermodynamic limit. Actually, by studying the real and imaginary parts, we can get a lot of useful information such as the residue of this pole. We have done the same for the BCM model, and we have a qualitative similar behavior in which the pole is actually in 1, because this is a dynamic phase transition rather than 0. Conclusions. So we have developed a linear response framework theory for the thermodynamic limit of weakly interacting diffusions. Using this linear response approach, we have identified 2 different types of criticality, critical transitions and phase transitions, and using a spectroscopy approach, which is related to linear response, we have been able to study the critical behavior of phase transitions even for finite systems too.